You know, if I told you there is a way to trick the human body into growing an entirely new functional network of blood vessels from scratch, you'd probably think we were talking about, I don't know, science fiction.
Right, yeah.
Or at least some highly classified experimental lab tech. But what if this incredible biological transformation is happening right now inside clinics using microscopic fragments of DNA sourced from fish?
It's wild to think about.
And it's being used to heal incredibly painful, damaged tissue in one of the most sensitive areas of the human body.
It really does sound completely like magic when you frame it that way.
Yeah.
I mean, we're looking at a process where medical science essentially, well, hands the human body a bucket of microscopic building blocks, steps back, and just watches the body completely rebuild its own infrastructure.
Yeah.
It's pure, elegant biochemistry.
It is so wild. So today we're bringing you a deep dive into a really unique stack of sources. We aren't just looking at one angle here.
No, definitely not.
We're starting with dense genomic data on human cellular receptors, moving through the deep tissue mechanics of how wounds heal, and then grounding all of that complex biology in real-world clinical trials that focus on postmenopausal vaginal ovules.
Yeah, and we need all those different lenses to really understand this. You have the absolute micro-level genetic data on one end, looking at, single molecules, and then the macro-level quality of life clinical outcomes on the other.
Right. And our mission today for you, the listener, is to map out this exact microscopic journey. We want to trace how applying these tiny fragments of fish DNA somehow forces the human body to produce a signal that acts as an architect to rebuild capillary networks.
Exactly.
And actually reverse a really severe condition known as ischemic vulvovaginal atrophy. Okay, let's unpack this.
Well, to understand how this treatment works, we have to first look at the environment it's trying to fix, right?
Yeah.
In this case, we were talking about the vaginal wall during peri and postmenopause, specifically an environment that has become ischemic.
Meaning a severe restriction in blood supply.
Right. Think about what maintains that blood supply in the first place. Before menopause, a woman's tissue is supported by regular, robust hormonal cycles. I mean, estradiol levels can peak at around 800 picograms per milliliter.
Which is a lot.
It's a huge amount. And that circulating estrogen acts as a maintenance signal. It keeps the vaginal epithelium, which is the surface lining, thick and well supplied with a really dense network of blood vessels.
Okay.
But during and after menopause, those estradiol levels drop dramatically, often falling below 30 picograms per milliliter.
Wow. So from 800 down to under 30. That is just a systemic shock to the tissue.
It is. The tissue essentially starves.
Yeah.
Without the estrogen signaling the body to, maintain that area, the vaginal epithelia flatten out. They lose these critical microstructures called papillae.
Right, the papillary.
You can picture papillae almost like the ridges on a piece of corrugated cardboard.
Right.
They provide surface area, stretch, and structural integrity.
Ah, okay, I see.
So when those flatten, the tissue thins out so much that the underlying connective tissue is dangerously exposed.
I kept picturing this like a dried out riverbed while I was reading the sources. When the blood flow basically dries up, the ground cracks, it becomes brittle, it gets easily damaged by even the slightest friction.
That's a really accurate analogy, actually.
And the clinical sources note this leads to things like petechia, which are these painful, tiny microbleeds, along with ulcerations. The vaginal health index just plummets, resulting in a lot of daily pain and burning for the patient.
Yeah, the vaginal health index measures elasticity, fluid secretion, pH, mucosal integrity, and moisture. All of those drop when the blood flow disappears.
But, if the problem is a lack of estrogen causing the drought, why not just add estrogen back? Hormone replacement therapy is everywhere now. Why go through the trouble of figuring out how to grow new rivers from scratch?
It's a great question. Traditional hormone replacement therapy is often a fantastic first-line treatment for many women. But not everyone can take systemic or even local estrogen. A patient might have a history of estrogen receptor-positive breast cancer, making HRT far too risky. Others experience severe side effects, or simply, choose not to use hormonal therapies.
That makes sense.
And sometimes, even with HRT, the local tissue damage is so profound, the microvessels have died off so completely that hormones alone just aren't enough to physically rebuild the structure.
So regenerative medicine has to step in to find a way to restore the physical structure and the blood flow without relying on hormones at all.
Exactly.
We need a different catalyst to bring water back to our dried riverbed.
Enter polynucleotides and polydeoxyribonucleotides, which are often abbreviated as PNs and PDRNs in the literature.
And this is where the fish come in. Our sources note these are highly purified, natural origin DNA fragments, primarily extracted from the gonads of salmon trout.
Yes.
But wait, I have to stop here. If you are rubbing or injecting salmon DNA into human tissue, doesn't the human immune system just freak out and attack it as a foreign invader? I mean, it's fish DNA.
What's fascinating here is that human cells don't read these specific purified DNA fragments as a threat, nor do they read them as a blueprint.
Okay.
They aren't trying to transcribe this material to make fish proteins. The purification process actually strips away the proteins that would normally trigger an immune response. What's left is just the raw nucleic acid,
Oh, I see.
and the human body acts like a highly efficient recycling center.
Meaning it just breaks the fish DNA down for spare parts?
Precisely. We call it the salvage pathway. Building DNA from scratch, synthesizing new purines and pyrimidines takes a massive amount of cellular energy. It requires a lot of ATP.
Right, it's expensive for the body.
Incredibly energy intensive.
Hmm.
But DNA is a universal biological language. The structural building blocks of salmon DNA are exactly the same as human DNA.
Okay.
So when these long chains of polynucleotides are applied to human tissue, they encounter enzymes called ectonucleotidases and nucleases.
The sources called these extracellular enzymes, so they're just, what, floating around outside our cells?
Yeah, they are anchored to the outside of our cell membranes, or just floating in the interstitial fluid. Think of them as molecular scissors.
The molecular scissors, got it.
When the long, dense fish DNA chains float by, these scissors chop them up into small, biologically active nitrogen precursors. Predominantly, they are broken down into a specific nucleoside called adenosine.
Okay, so the salvage pathway grabs this adenosine because it's way cheaper than making it from scratch.
It's much cheaper energetically, yeah.
Yeah.
But recycling is only part of the story. More importantly, the human body uses that chopped up adenosine as a chemical messenger.
So we've got the fish DNA broken down into adenosine, flooding this dried out, starved vaginal tissue. Now we need to trace exactly what happens when that adenosine starts trying to talk to the human cells.
Right.
And the NCBI data gets incredibly specific here about where it binds.
It really does. The
Yeah.
release adenosine selectively targets specific receptors sitting on the surface of local human cells. We're talking fibroblasts, macrophages, and endothelial cells. We are particularly interested in the adenosine A2A receptor and the A2B receptor. In the genomic databases, the A2B receptor is coded as ADOR A2B, located on human chromosome 17.
Okay, adore A to B. Let's unpack how a receptor actually works for a second. The adenosine floats up to the cell membrane and hits this ADOR A to B receptor. What actually happens?
So these are G-protein coupled receptors. You can imagine the receptor as a complex doorbell that passes all the way through the cell's outer wall.
A doorbell.
When the adenosine binds to the outside portion, it physically changes the shape of the entire receptor. That shape change reaches inside the cell and pokes a specific protein, the G protein, waking it up.
It rings the doorbell, and the G protein is like the dog inside that starts barking.
That's one way to look at it, sure.
Yep.
That activated G protein then kicks off a massive internal signaling cascade. It turns on an enzyme called adenylate cyclase.
And what does that do?
It has one job, basically.
Yeah.
It turns out a molecule called cyclic AMP, or KIR-AMP.
Ugh, CAMP. I've seen CAMP pop up in other deep dives. It's basically a universal internal alarm system for the cell, right?
Exactly. It is a critical secondary messenger. A spike in CAMP tells the cell that something major is happening outside. In this specific pathway, that rise in CAMP promotes a process called phosphorylation on a transcription regulator known as PCREB.
Okay, we have to translate that. What does phosphorylation of PCREB actually mean for the cell?
Phosphorylation is basically the cell handing a worker a hard hat and an assignment. By adding a phosphate group to PCREB, it activates it.
I like that analogy.
This activated PCREB acts as a master key. It travels directly into the cell's nucleus, binds to the DNA, and literally starts flipping genetic switches on and off.
Here's where it gets really interesting, because the switches that this master key flips completely change the tissue's immune profile. It essentially hacks the body's inflammatory response.
Yes. In a chronic wound or in severely atrophic tissue like our dried riverbed, you have a massive accumulation of what we call M1 macrophages. These are pro-inflammatory immune cells. Their job is to fight infection and clear debris. To do that, they secrete harsh chemicals like TNF-alpha and interleukin-6, which keep the tissue in a state of chronic, painful inflammation.
It's like having a demolition crew permanently stationed in the tissue just tearing things up, and they won't leave. Why does the adenosine make them stop?
This is one of the most beautiful mechanisms in biology, honestly. In nature, when cells are severely damaged or dying, They spill their internal contents, including a massive amount of ATP.
Right.
As that ATP breaks down in the extracellular space, it becomes adenosine. So high levels of adenosine act like a chemical ceasefire flare.
A ceasefire flare. Wow.
When the macrophages taste that adenosine via the ADOR-A2B receptor, they interpret it as a signal that the acute damage is over, the battle is done, and it's time to rebuild.
That makes so much sense. We are artificially flooding the zone with adenosine from the fish DNA to trick the demolition crew into thinking the war is over.
Exactly. The scientific term is shifting the macrophages from the M1 phenotype to the M2 phenotype.
M1 to M2.
The M2 cells stop pumping out the inflammatory TNF-alpha. Instead, they aggressively upregulate anti-inflammatory cytokines like interleukin-10. And most importantly for our ischemic tissue, they start pumping out vascular endothelial growth factor.
VEGF, the architect of our new blood vessels. So just by applying these DNA fragments, the molecular scissors chop them into adenosine, which rings the ADOR-A2B doorbell,
Right.
which sends the PCRE master key into the nucleus, which fires the ceasefire flare, calming the inflammation and flooding the area with the exact signal needed to grow new capillaries.
You got it perfectly.
Right.
But having the architectural blueprint is only half the battle. VEGF is just a chemical messenger. The tissue now has to physically construct a new microvascular capillary network out of the existing starved vessels.
Right, the VEGF is blowing the whistle, but the workers still have to build the road. And the sources detail exactly how this happened through a process called sprouting angiogenesis.
Yes, and this process is incredibly tightly controlled. It relies heavily on a specific isoform, a specific shape of VEGF called VEGF 164.
The research highlighted a really specific detail about VEGF 164 having a heparin-binding motif. Why is that so crucial? If the cell is pumping out this growth factor, why doesn't it just float away into the bloodstream?
Well, if it floated away, the new blood vessels would grow in random directions, which could lead to malformations or even tumors.
Oh, yikes.
Right? So the heparin binding motif acts like a patch of sticky molecular Velcro. As soon as the cell secretes the VEGF 164, it immediately gets snag on the extracellular matrix, which is the web of proteins sitting between our cells.
So it gets stuck.
Exactly. It doesn't wash away in the interstitial fluid. It stays exactly where it was produced, creating a very steep, localized chemical gradient.
Meaning the concentration of VEGF is highest right where the tissue is the most hypoxic, the most starved for oxygen, because that's where the macrophages are pumping it out.
Yes. And the endothelial cells, the cells that line the inside of our existing damaged blood vessels, can sense this gradient. This initiates what biologists call the tip and stalk cellular dance.
The tip and stalk dance. Okay, I was trying to visualize this while reading the research. Tell me if this analogy works. It's like a road construction crew pushing through an unmapped wilderness. The tip cell is the lead surveyor with a compass.
That is a remarkably accurate way to picture it, yeah. The endothelial cell that becomes the tip cell develops these long, finger-like projections called filopodia.
Filopodia, okay.
And these filopodia are packed with specific receptors called KDR or VEGFR2. These act exactly like the surveyor's compass. They're constantly reaching out, sensing the environment, feeling for that sticky VEGF Velcro.
Wow.
And they are physically dragging the cell toward the highest concentration of the signal, straight into the most ischemic areas.
So the tip cell is out front, blazing the trail, pulling itself toward this chemical ceasefire flare, but a single cell stretching itself out doesn't make a hollow tube for blood to flow through.
That's where the stalk cells come in, right?
Exactly. The stalk cells follow right behind the tip cell, but their job isn't to navigate. Their job is to build the actual infrastructure of the pipe. They are the paving machines laying down the asphalt behind the surveyor.
Yeah, and they don't just lay it down. They have to physically multiply. As they follow the tip cell, the stalk cells proliferate. And as they multiply, they go through a process of vacuolization.
Vacuolization.
They literally hollow themselves out from the inside to form the lumen, the physical tube of the new capillary.
That is amazing. If you're listening to this, you have millions of these microscopic construction crews working inside you right now, perfectly coordinating without a single brain cell.
It's incredible.
But how do they communicate? Like, how do the cells know who gets to be the surveyor and who has to be the paving machine? Why don't they all just try to be tip cells and branch off in 100 different directions?
It's controlled by a secondary communication system called DLL4-NO-TCH signaling. This relies on contact inhibition.
Contact inhibition.
Yeah. Once a cell commits to becoming a tip cell, it expresses a protein called DLL4 on its surface. When that DLL4 physically bumps into the NO-TCH receptors on the neighboring stalk cells behind it, it sends a suppression signal. It's essentially the tip cell reaching back, touching the stalk cell, and saying, I'm driving. You focus on building the tube.
It is unbelievable how beautifully orchestrated that is. We go from fish DNA, chopped into adenosine by molecular scissors, hitting the ADOR A to B receptors, spiking CAMP, sending the pCRA master key to flip the immune response,
Right.
dropping a sticky VEGF gradient to a perfectly coordinated construction crew of tip and stalk cells physically building a new capillary.
If we connect this to the bigger picture, we have to bring this out of the microscopic world and back to the macro-level reality for the patient. What does this new microvascular network actually do for the atrophic, painful vaginal wall?
It finally brings the water back to the dried riverbed.
It restores blood flow. And with that blood flow comes a massive influx of oxygen and nutrients. This sudden delivery of resources revives the local fibroblasts, which are the maintenance cells of the connective tissue.
Right.
They've been sitting dormant, starved in the tissue for months or years.
And fibroblasts are the factories that manufacture collagen and elastin, right?
Yes. They wake up and start aggressively pumping out fresh type I and type 3 collagen, along with new elastin fibers. The tissue physically rebuilds its own scaffolding. It becomes thicker, more resilient, and deeply hydrated from the inside out.
Wow.
The papillae we talked about earlier, they begin to reform.
Which brings us to the real-world clinical data. We aren't just talking in theory here. We have a study of 54 women who were suffering from severe vulvovaginal atrophy.
Yes, a very important study.
They used these polynucleotide-based vaginal ovules for just a few weeks, and the results on that vaginal health index we mentioned at the start are staggering.
The clinical outcomes directly mirror the microscopic mechanism we just described. When you rebuild the capillary network and wake up the fibroblasts, the macro-level symptoms inevitably resolve.
Over a few weeks, these 54 women saw a 59.8% improvement in hydration, a 52.7% improvement in vaginal secretions, and a 51.6% reduction in those painful superficial petechia, those microbleeds.
And the microbleeds stop because the tissue's no longer paper-thin and fragile. It has structural integrity and a healthy vascular bed again.
And maybe the most impactful stat for daily quality of life. Vaginal burning decreased by a massive 72.5%. I mean, for a patient dealing with constant daily pain, a 72% reduction in a matter of weeks is life-changing.
It's a profound relief of symptoms. And it's worth noting how these treatments are formulated. In a lot of these clinical applications, the polynucleotides are paired with hyaluronic acid, or HA.
The sources mention the synergy between PNs and HA. Why do they need to be paired?
While the polynucleotides are doing the heavy lifting of rebuilding the structural pipes, the capillaries, and the scaffolding, the collagen, that biological construction project takes time, angiogenesis doesn't happen overnight.
But the patient is in pain today.
Precisely why the HA is included. Hyaluronic acid acts like a massive molecular sponge. It immediately binds to water and holds it in the extracellular matrix.
Oh.
It provides fast, soothing relief and lubrication right away. It bridges the gap, keeping the tissue comfortable while the longer-term vascular regeneration driven by the PNs takes place.
So the HA puts out the immediate fire while the PNs rebuild the fire station. That means we aren't just masking symptoms with temporary moisturizers or lubricants. We are fundamentally reversing the biological age and the functional capacity of the tissue itself.
That is the ultimate promise of true regenerative medicine. You are changing the physical reality of the tissue.
Yeah.
You are restoring it to a premenopausal state of function, not by forcing synthetic chemicals into it, but by speaking directly to the body's own cellular machinery in a language it already understands.
It really is an incredible journey. Just to recap how far we've come, we started with a menopausal drop in estrogen that causes the tissue to starve, flatten out, and become ischemic. We introduced microscopic DNA fragments from salmon trout. The body's extracellular enzymes cleave them down into adenosine because recycling is energetically cheaper. That adenosine rings the ADOR A to B doorbell on the cell surface, kicking off an internal alarm cascade that sends a master key to the nucleus.
Exactly.
This flips the immune system from destroying tissue to healing it, firing off a ceasefire flare. That healing phase floods the area with a steep, sticky gradient of VEGF. The VEGF acts as a compass for tip cells to blaze a trail, while stalk cells pave a hollow capillary tube right behind them.
The perfect summary.
And finally, that new blood supply brings the oxygen needed to pump out fresh collagen, clinically restoring the intimate health, comfort, and structure of the patient.
It is a masterclass in how understanding the deepest levels of cellular biology allows us to leverage the body's own profound evolutionary capacity for self-repair.
So what does this all mean? It means relief for millions of women dealing with vulvovaginal atrophy who can't or won't use traditional hormones. But it also leaves you with a pretty massive question. If manipulating this adenosine VEGF pathway can successfully trick oxygen-starved atrophic tissue into growing its own fresh blood supply from scratch, well, where does it end? Could localized DNA fragment transfer eventually replace traditional invasive vascular surgeries entirely?
That's a fascinating thought.
Could we one day stop doing skin grafts for severe burns and instead just paint the wound with the exact chemical language needed to tell the body to build new skin and blood vessels itself? We are no longer just treating the dried out riverbed. We've figured out how to command the earth to open up and build a new river. Thank you for joining us on this deep dive. Keep questioning, keep exploring the microscopic wonders of human biology, and we will catch you next time.